Let's say I want to add a basic timer in my application. I would like to have a countdown that will print the numbers from 100 down to 1. To test this, I'm going to simply log my messages before actually showing the countdown on my application's user interface. So I'll simply take this it to string, and this is going to count from the low index to the high. So I'm going to do a 101 minus a 100 minus, and that will starting by subtracting 0, then subtracting 1, then subtracting 2. So if I run my application and I check my log, I should see my timer. And there it is. Now you might have missed it. Here it is. Not much of a timer, you would imagine, since I got all the numbers, but we missed it. It was almost instantaneous. If I did that again, we'll see that as soon as the application launches, it runs through my timer, because this is just a basic loop. This repeat function just implements a for loop, and it counts from 0 up to 1 less than this number. And the reason we're not seeing anything, of course, is because there is no pause in between each iteration of this loop. If I wanted to do a pause here, it would be relatively straightforward. All I would really need to do is tell this thread to sleep for a certain number of milliseconds. So 1000 milliseconds would be 1 second. This statement is essentially pausing my application's main thread. A thread is a unit of execution. Every application has at least one thread that we call the main thread, or you may hear it referred to as the UI thread. The reason it's called the UI, or user interface thread, is because, unless you otherwise specify, the main thread is responsible for executing your code, but it is also responsible for drawing your user interface and responding to events that occur. So clicking on views, etc., is processed by your UI thread. Now, by pausing the UI thread, when my application runs, we're going to notice a couple of things. First, we're going to see that my timer feature now looks pretty reasonable. I see that there is a pause happening at every stage. But you'll notice over in the emulator, my application seems to be in this limbo state where I'm not seeing my user interface. Instead, I'm simply seeing this vague screen that doesn't represent my actual UI. The reason I'm seeing this screen is because the UI thread, the main thread, is being kept busy. Whereas we saw before, this block of code could be executed in a fraction of a second, thereafter freeing up the thread to do other things like drawing my user interface. By forcing my thread to sleep, I am essentially preventing that thread from doing any other work. So instead of doing things that need to be done, like processing UI draw statements or operations, I'm instead having it just sit idly for an entire second after each iteration through this loop, which for a processor is a large amount of time. So this is a wasted operation. My application is non-responsive, and all of this just to have a timer. Now, once the timer runs out, there you can see my application UI is now drawn in and we can continue as usual. But you can easily see why this is less than ideal. Essentially, if I want to do something like implement this particular operation, it is not sufficient to use thread.sleep on my main thread. The traditional solution to this problem is to essentially build a multi-threaded application. What I could do here is spin up a worker thread and essentially introduce asynchronous operations into my application. By creating a worker thread that is responsible for performing this countdown, I would free up the UI or main thread to do everything else that it would normally do. And this background thread or worker thread could print information to the log or do any other kind of work without interfering with the main thread. Now, in modern versions of Android, instead of using the low-level thread library that is available to us, Android has introduced a new mechanism to perform these types of asynchronous operations. Today, we're going to talk about coroutines. We're going to look at what a coroutine is. We're going to talk about some of the specific characteristics of coroutines, such as coroutine scope and context. And then we're going to look at dispatchers, essentially determining which thread a coroutine will execute on and how we can switch between those dispatchers. So first up, what is a coroutine? Well, simply put, a coroutine is a suspendable computation unit. That essentially means that a coroutine can have its execution suspended, or if you'd like to think of it, paused. And that pausing of the execution of a coroutine allows another coroutine to be executed, essentially incorporating a type of time sharing, where instead of a thread being blocked by a particular coroutine when it's not doing anything, that coroutine can be removed from the thread, a new coroutine brought on, and it is allowed to execute. So we don't have the case where a thread is wasting time in a sleep state, not when there's actually work that needs to be done, defined in another coroutine. When dealing with threads, an application can become relatively complex. Not only do you have to be concerned with just how many threads are executing and the resources it would take, additionally, you have to worry about the coordination and have concerns with things like memory leaks. When operating with coroutines, they're oftentimes thought of as lightweight threads, in part because it takes care of some of the concerns that we tend to have with threads. But at the end of the day, working with coroutines can be a little more straightforward than dealing with low-level multi-threaded applications. So when dealing with coroutines, one of the first things you have to make decisions on is what is the scope of the coroutine. A scope essentially defines the lifetime of the coroutine. How long should it run? So this is similar to the way a variable, for example, can be in or out of scope. So a variable defined inside of a function will exist for as long as that function is executing. When the function exits, so does the variable. Kotlin by way of specific extensions, can provide predefined scopes. However, we can always create our own scopes by providing what's called a coroutine context. Coroutine context are a set of elements that determine how the coroutine will execute. When creating your own coroutine context, you can optionally provide a job, where a job is essentially what executes a specified block of code, and it takes that code execution through a set of state transitions from its initial active state all the way to its completed state. A dispatcher can be specified to essentially dictate which thread the coroutine should execute on. And there are three dispatchers. The first is the main dispatcher. This will execute code on the main thread. The main dispatcher is useful when you are executing non-blocking operations and when you need to access view elements. A non-blocking operation is an operation that is either quickly executing or asynchronous in its execution. That is, it will not pause and wait for the return of a function. It will simply continue executing the rest of your statements. If a statement is blocking, that means a call to a function or attempting to execute or evaluate an expression forces the thread to wait until the execution is completed for some extended amount of time. And it is generally a good idea to not place blocking code on your main thread. The I/O dispatcher is used to perform input-output operations. So operations that, for example, go out to the internet, or that might read or write files or databases, are considered I/O operations. And we have a specific dispatcher, a specific thread that is used for those types of operations. The default dispatcher is used for doing processor-intensive tasks. So think of things like cryptography or sorting large data sets. Things that involve a lot of number crunching, a lot of data manipulation that can take some amount of time, but don't necessarily require access to the view system and do not touch files or databases. We place those types of operations on the default dispatcher. So let's look at our example and see how we can utilize coroutines to recreate this feature. So before we can do anything with a coroutine, we sort of have to define a scope. A scope for us can be created with a coroutine scope, where we can specify context by specifying a job and a dispatcher. So a job can simply be specified by invoking the job constructor, and we can specify a dispatcher from our list of dispatchers. In this case, let's say my timer is a number crunching intensive operation. So we say that we'll do this on the default dispatcher. Now that I have a scope, I can execute a coroutine by launching this block of code and placing my timer code inside this block. At this point, we have one change that we will need to make. Instead of calling thread.sleep, what we would like to do is use the coroutine version of that operation, which is to call delay. And we can delay for 1,000 milliseconds, essentially giving us the same outcome as forcing the thread to sleep. So this essentially is equivalent to my initial code. The difference being, you can see that while my timer is in fact counting down, my application's user interface is fully drawn in. Because now that I'm using coroutines, when my coroutine is delayed for 1 second, the thread on which the coroutine is executing, and in fact the other threads in my application, are not held up. Instead, they're able to do work, even the default dispatcher, in the case where this element is paused or delayed for a period of time. Now, if I wanted to put this functionality not in line as I have it here, but in a function, I could do that by simply defining a function. And I would like to move my code directly into said function. However, I can see that I have a slight error here, and that is this delay function has no meaning in countdown timer. The reason is, whenever you're going to invoke a function or define code in a function that incorporates coroutine specific functionality, that function must be suspendable. And I make a function suspendable by using the suspend keyword. Now, I can simply call countdown timer from within my coroutine, and I get the same result. Now, let's say that having tested everything and I'm convinced that my countdown timer functionality does everything it's supposed to, I now want to display my countdown in the user interface. Well, let's first make this text view, let's give it an ID. So I'll just call this countdown, or let's call it timer text view. And I will make it a little larger so that we can better see it. All right, and this will have a default value of 100. When the application begins. All right. My goal then is to first define this text view and then in my countdown timer, in addition to logging or instead of logging, I may decide I'd like to set my timer text view text value to be this same value. So I could then simply say so I'll take that value and in addition to printing it, I will also display it on my text view. Running this application, the result is a crash. You can see that one more time. So why is my application crashing? Well, it's crashing because of this exception, called from wrong thread exception. Why am I getting this exception? Well, the message gives us a hint. Only the original thread that created a view hierarchy can touch its views. What this is essentially saying is that the only thread that is able to manipulate a view object is the UI thread, or the main thread. Here, we are attempting to update an attribute of our view object, but this is being done from the default dispatcher. The default dispatcher is not executed on the main thread. If I need to update my view, what I could do is execute this on my main thread instead of the default dispatcher. Or if this was being done on the IO dispatcher, I could switch again to the same thing. Now, this would work. If I now execute, I'll see that I'm getting the timer exactly as I would like, both in my log, but also in my UI. But there's a problem here. It's a problem that I'm making up, but this is something we could face in real life, which is if I've said to you that this code is something that should in fact be done in the default thread or the default dispatcher, or let us say that this was something that was accessing the internet, which means it needs to be done in the IO dispatcher or the IO thread, then simply changing the dispatcher to main wouldn't work. In fact, in some instances, it may cause my application to crash in the worst case, and in the best case, it may cause my application to be slow and unresponsive. So it's not sufficient to just switch the dispatcher to main and say, well, that allows me to access the UI, so we have no problem. Instead, I need a different solution. When dealing with coroutines in Android, we actually have the ability to switch contexts within a single coroutine. That is, once we've launched a coroutine within a given scope, we can have different aspects of that coroutine be executed on different dispatchers. This can create very streamlined and easy to read code because we can see in line where a context switch occurred and what code is being executed, instead of using callbacks, which might force us to scan to different areas in our code to see exactly what a particular callback is executing. To perform a context switch, we use the with context function, where we then specify the block of code that should be executed on a given context. So let's see how we can implement our timer application by incorporating context switching. So we can go back to the default dispatcher for our coroutine scope. As a reminder, because we're executing in the default, our application will crash at the time it tries to access the view system. Our goal then is to tell Android via context switching that this specific line of code should not be executed on the default dispatcher. Rather, it should be executed with main dispatcher. At that point, this keyword refers to the coroutine scope. So I'd have to change this to say I'm referring to the run. So this allows me to access this string here, whereas before this was referring to the context, or rather to the coroutine scope. So now we can execute our code and we can essentially access the view system, but instead of having the entire coroutine executed on main, which we have said before we don't want to do, or in some cases we would not be allowed to do, we're able to simply switch to a different dispatcher only for this line of code. And you can see how contained and easy to read this is. No callbacks or anything else, which we might have been forced to use had we implemented this timer using the standard low-level thread operations that are available to us. So this is the most basic of introductions to coroutines. There are more considerations as it relates to using coroutines with predefined scopes, using coroutines in different contexts or different components, utilizing coroutines with life cycles and view models. There are, in fact, quite a few considerations. But just to get up and running, dealing with coroutine scope, coroutine contexts, jobs, and dispatchers gives us the basics to get up and running.